All right. Okay, so it is my very great pleasure to introduce today's speaker, Professor David Srolovitz. So David obtained a PhD in 1981 in material science from the University of Pennsylvania, and then moved on to become a postdoc at Exxon, followed by a position at Los Alamos National Lab. Then he went on to become a professor at Michigan, later moved on to Princeton. After that, I believe he became dean at Yeshiva University, then took up a position as executive director at A-Star in Singapore of the High Performance Computing Institute, before coming back to the US to work as professor at the University of Pennsylvania. And I think now he also has a joint position at the City University of Hong Kong. So a man that certainly has gotten around quite a bit. His work is on theoretical and computational studies of the structure, properties, formation, and evolution of solid state materials. And he's really looking at these systems, you know, from the atomistic scale all the way to the continuum scale, looking at growth, microstructure, with a variety of techniques. So he has, I believe, more than 500 papers. His H index currently is around 100. He happens to be one of the top 2 most highly cited scientists. Of course, he's won a lot of prizes and awards, which I won't even mention, because I guess we all want to hear from him about his work. So David, please go ahead.
Okay, well, first let me see if I can share my screen. Get this all set up. Just a moment.
Okay, that works.
Okay, very good. Okay, so first I'd like to thank the organizers for inviting me back to the Thomas Young Center. I have to say I'm a bit disappointed that I have to do this online, because I would much rather be in London right now. But I guess that applies to a lot of us that we love to travel. Okay, so what I'm going to talk about today is some work that we're doing right now. And as I was mentioning before the talk began, this is the first time I've actually had an opportunity to present it. The work tries to address the question of metastable crystal structures that can coexist and that only occur when you make a material strong enough. Okay, so let me explain what that means in a few minutes. I should say that this was work done with Dr. Subbu Padamada, who I should say he's the one who actually did the work, and I get to talk about it. Okay, so here we go. So normally when we think about stress-driven phase transitions in materials, we usually start by thinking about diamond anvil kinds of experiments. And, so the effect of pressure on phase transitions is well known. Metals, semiconductors, ceramics, we know about phase transitions in all of these as a function of pressure. And, I put in here some nice pictures of some of the classic experiments. On the top here, these are diamond anvils. This is a diamond anvil cell. Just point out a few things about this. So what happens is you squeeze on it, put a force on it this way by tightening the screws. There's a gasket that goes around here. You sample sitting in there, and there's usually little rubies in there which have a fluorescent line that shifts with pressure. And so by shining light or X-rays in there, we can understand the structure of the material and also measure the pressure. You can also do this dynamically, and people use gas guns or explosives like shown over here. or drop tubes. There are many ways to put on very high pressures. And even though these are dynamic experiments, I'm really going to be focusing on pressure for the moment. And we'll talk about strength issues later on. And in particular, what I'm going to be talking about is diffusionless phase transformations. And just to give you a few examples, if you look at iron, if you at low temperature, so iron's body center cubic, as we all know, under normal atmospheric conditions, in room temperature, if you squeeze on it hard enough, it goes into the epsilon phase, which is HCP phase. And it's obvious why it does that, because the close pack structure there is higher density. So when you squeeze on it, you thermodynamically shift the phase equilibrium. And if you do DFT calculations, you can estimate the transition should happen at about 10 GPa, but the experiments typically show some higher value, and I'll come back to that in a minute. Okay, so if I look at other materials, zirconium goes through a hexagonal close pack to a different hexagonal structure, room temperature at about 2 GPa. Silicon goes through a whole large range of phase transitions, including a diamond to beta tin type structure at a pressure range of 9 to 16 GPa. So a couple of things to note about it. First, the stresses that we're talking about are a little bit high, 13 GPa. That's normal. That's beyond what we as material scientists normally would experience on a routine basis. And so this has been sort of part of the field of high pressure physics. And it's an interesting topic all by itself. But really what I want to think about today is what happens when the stress state is not completely hydrostatic, not just pressure. I mean, as you may be aware, stress tensor has more than one component. So therefore, we can start asking what's going on with these other components. We also ask why we haven't really looked at it very carefully before. Okay, so what are some of the indications that these non-hydrostatic stresses are important? Well, the first one is that if you look at the transformation pressures, typically they show a very large range of transformation pressures, even in materials of almost very high purity materials. And as I'll show you in a little bit, it depends on the pressure medium. So the pressure medium shown here in this light blue color, and that pressure medium is the thing that when you squeeze on this, when you push down, you pressurize the medium, and that medium then pushes on the sample. And if you change the medium that you use as the pressure medium from helium gas to argon to sodium chloride to sapphire, the pressures that you get the transformation and the range of pressures over which you see the transformation can vary dramatically. Okay, so we'll come back and we'll think about that in a little bit. So at this point, the thing to know, oh, and by the way, it also works for the reverse transformation. Now, if you do a DFT calculation, this is for iron, and this is from some work by Johnson, and you get a pressure transformation by 9.56 GPa, which is reasonable. So 9.56, so just to get kilobars to gigapascals, it's like a factor of 10. Okay, so the point is, as you go to higher and higher strength pressure media, you're getting larger and larger scatter. The yield stress of helium is very low, right? It's basically zero. And so you have a very small range of measured values. On the other hand, as you go to a material that has a very high yield stress, the range of pressures that you see gets very large. And so people have for a long time attributed the scatter to non-hydrostatic stresses, and we'll talk more about that. People have also created what they call a rotational diamond anvil cell. So that's shown here. It's just like the original one, except you twist one diamond relative to the other about its axis. And if you do that, what you can find is that you can get a pressure distribution that is from the center of the diamond anvil cell that looks sort of like this. And so if you have a stress, you have a pressure gradient, that implies that you have a shear stress. And so what they're doing is they're controlling the shear by the twist that they apply. Okay, so that's an observation. And by the way, this is not just iron. You see the same sort of spread in values if you look at titanium, zirconium, hafnium, silicon, boron, nitride, and the list just goes on and on and on. It's actually fairly rare to get just a, if you repeat the experiment, or different groups repeat the experiment, you get a range of values. Okay, so that's what I just told you. So shear stresses seem to have a large effect on transformation pressures. And if I look at some examples, so here's a high entropy alloy. I figured to start with something recent. In this particular alloy, if you look at what the transformation pressure is from FCC to hexagonal closed pack, it goes between 7 and 50 GPa. That's a very big range. Okay, if I go to boron nitride, if you do it under hydrostatic conditions, you get a transformation of about 53 GPa. On the other hand, if you do it in one of these rotational or torsional diamond anvil cells, it goes down by a factor of 8 or so. Okay, so these are big effects. Iron, BCC to HCP, the alpha to epsilon phase transition, large scatter. Okay, so that's what I just showed you before. Zirconium has, more than a factor of 10 in scatter. Silicon goes through a whole range of transitions as you increase the pressure, from diamond to beta tin to what's that? The bodies centered tetragonal crystal, hexagonal, et cetera, et cetera. And the interesting thing is all of those transformation pressures for each of those phase transitions seems to depend on shear stress. Okay. Let me show you some recent data on some polycrystalline nickel from the group in Shenyang, IMR. So first, let me just remind you about nickel. If you take nickel and put it under hydrostatic stress to very high pressures, it just stays FCC, and the estimate is up to about 200 GPa and all the way up to the melting point. I'm not sure I believe the 200 GPa number, but the point is that nickel really wants to be FCC and nothing else. Okay, but now some work out of the Shenyang IMR is kind of interesting. I'm going to spend a little bit of time on this. In fact, talking to Luke Hood, this is what sort of motivated me to actually start to look at this. It just took me a couple of years to do it since he showed me the original experiments. Okay, so what they do is they do a surface mechanical grinding experiment. So they take a sample, like a cylindrical sample, and they press down on it with a rounded tip like this. It's tungsten carbide in cobalt tip. And they put a pressure on it, so pushing down onto the cylinder normal to its axis, and they rotate it. And they just go through the material and deform a layer near the surface. And what they end up with is, if you look in a radial direction around this cylindrical sample, is you end up with a gradient in grain size that goes from about 60 microns in the bulk of the sample to just a few nanometers near the surface of the sample. Okay. Now, why do I bring that up? Well, it's because if you actually look at this sample, like the IMR group did, what you'll see is that some of the grains in the sample, entire grains, seem to be hexagonal close packed instead of FCC. Okay? And so here's some of the experimental observations. It's a little hard to see this, but this is just looking at the microstructure on a very large scale. If you look 4 microns below the surface, you can start to see small grains here, 10 nanometers, a little bit bigger than 10 nanometers, and a grain size distribution shown on the left. And they also went in and did micro hardness measurements. And when they did the micro hardness measurements, they find as they get closer and closer to the surface, where the grain size is small, the micro hardness goes up and the values up to close to 9 GPa. Okay? And it's not surprising that as you go to smaller and smaller grain sizes, you get larger and larger strengths or hardnesses. And you know, if I make the argument that hardness and yield strength are, you know, a factor of 3 apart, which is very hand-waving, that suggests that the material there has a yield strength of around 3 GPa, corresponding to the 9 GPa of the microhardness. Okay, well, so that's interesting. So shear stresses after grinding can be as up to the yield stress. So if I make the assumption that I've got stresses in the material up to whatever the yield strength is of the material, then I can sort of start asking the question, what do these large shear stresses do? Okay, and so here's actually a few more images, which I think are quite beautiful. You got a beautiful microscopy. Okay, so what they're showing here on the upper left in the high resolution TEM image is they're showing a region of the material, and if you can go in and look at the atomic structure and show that it's hexagonal, or if you do the electron diffraction from it, you also see all these peaks which you can index as hexagonal. Here's another region here. This is a 2 nanometer scale, and this grain here, it's an entire grain, indexes to a hexagonal close packed material, and the grain right next to it indexes to an FCC material. Okay, and if you actually go in with X-rays, and if you go in and actually try to measure the lattice parameters from the spots, you'll find out that if you look at different regions of different grain size, you always have things which are face-centered cubic with a lattice parameter around 3.5 angstroms. But you also start to pick out peaks associated with the A and C axis of the hexagonal close packed material. So the first thing I want to note here is that the transformation or the hexagonal material seems to be entire grains, not just along a single stacking fold or a small number of stacking folds in the material. It seems to be entire grains transformed. And you know, since this is close to the surface, there's no normal stress because of the zero traction boundary condition. And so that would suggest that the stresses there are shear or biaxial or something which is not hydrostatic. Okay, so this is a case where the hydrostatic stress is relatively small. Okay, so let me state the problem and then we'll go about ask how do we solve the problem. So the first question is, how does stress affect phase transformations? Okay, it's a very old question, but more specifically, I'd like to ask the question, what is the effect of the entire stress tensor on phase transformations? Okay, so we're not just asking about the pressure, which is the scalar. I'm looking at all components of the stress. And the question is, why didn't somebody ask and resolve this question 50 years ago? Well, there's actually been quite a few people who have looked at this over the years. But I would say it really hasn't been a very serious question up until now. And the real reason for it is that in materials, large non-hydrostatic or shear stress, as a general rule, have been inaccessible. And why is that? Well, very simply, as compared to these large hydrostatic stresses we can apply, metals tend to have yield stresses which are much, much smaller than the values that I was quoting before. Okay, and if I'm not dealing with metals, many materials with large shear stresses will just fracture at, before you get up to very large non-hydrostatic stresses. So the main issue has to do with the fact that in practice, it's very difficult to put on very large shear stresses. So to achieve these very large non-hydrostatic stresses, what we can do is start thinking about some of the ultra strong, ultra high strength metals, or metals which are near phase instability. So some of the high entropy alloys are near phase instabilities. And in the nanocrystalline metals, like the example I showed you before, nickel, or other nanoscale microstructures, you can really achieve stresses which start to approach the theoretical strength of the material. Okay, so therefore, you're only going to see these kinds of effects I'm talking about today when you have, in metals, nanostructured materials or extremely high strength metals or materials which are very close to instability. So there's two ways to do it. Okay. So let's talk a little bit about thermodynamics of solids. So what I'm going to do is look at a phase, parent phase, which we'll call alpha, and is subject to a general uniform stress, which I'll call sigma. And unlike the pressure, the stress is a 3x3 tensor. So it has 6 components. Okay. So we've got to do this problem nominally in 6 dimensions. Okay, we'll talk about how to simplify it a little bit. And then we want to say, well, this thing will transform into a daughter crystal structure to another. It'll transform from the parent to the daughter. And we'll call the daughter phase, we'll call that beta. Okay, so we've got an alpha possibly transforming to beta. And in principle, the relative orientations of alpha and beta is arbitrary. It could be any orientation. That's an SO3. Okay, so you got a 3-dimension, you got a 3-parameter rotation. But on the other hand, and by the way, we started by doing this in DFT, exploring over all of SO3. But what we find out very quickly is the classic orientation relations for these phase transitions really do work. Okay, so I'm not going to bore you with showing you how to do the calculations for all possible grain orientations, but we're just going to stick with a few of the well-known orientation relations. Okay, so we're talking about low temperature, so let me talk about the enthalpy or the free energy, the same thing really. And so if I have a linear elastic solid under stress, then the enthalpy is just the internal energy and times whatever the strain energy is. And if it's linear elastic, it's simple, like I showed there. If it's a nonlinear elastic body, still do general elasticity. So replace that simple stress with the Piala-Kirchhoff stress and the strain with the general strain deformation gradient. Okay, there are ways to do it. I'll show you a little bit more later on. Okay, but that's how it looks for the simple stress crystal. Okay, that's no surprise. It's linear elastic. Okay, now let's look a little bit more carefully. And again, I'll stay with the idea that it's linear elastic for the moment, and then we'll go beyond that. Okay, so the change in enthalpy, or in this case, I'll call it free energy, is just the difference in the energy of the alpha and beta crystal at zero stress minus the change in the strain energy. So delta S is the difference in the compliance of the alpha and beta phases. And sigma ij, epsilon ij, tr is just the stress you apply time with a product with the transformation strain. And this transformation strain is a stress-free strain that takes you from the alpha phase into the beta phase. Okay, so we can do that just by crystallography. Okay, so that's the transformation strain. And again, this is still linear elastic. Now, as you can imagine, if you're going to be doing this and you're going to be approaching strengths or stress levels, which are comparable to the theoretical strength of the material, then linear elasticity is not going to be very good. And so what we're going to have to do is do something beyond that. And so what we'll do is we'll calculate the energy of the stressed crystal. We're going to specify the stress. We're going to find the energy of the stress crystal with DFT. So the way we do it in practice is you figure out what strain you have to apply to get that stress, and then you do the optimization to get the stress, which is your target. Okay, and then there's the transformation part here. Okay, so this part here, that we do with DFT. An alternative is you can just take this free energy and expand it to higher and higher order in the elasticity. So if I want to do nonlinear elasticity, here I've written it up to third order in the elasticity. And as I'll show you, this third order elasticity actually does a pretty nice job for the problem that we're going to be talking about today. But let's wait until I show you some data to convince you. Okay, so stress. Stress has 6 components, right? We can decompose it into a hydrostatic part that's written here. So this is along the trace, and this is the deviatoric stress, the shear stress. So it's just the actual stress minus the identity times the identity matrix times the pressure. Now, I'm going to show you a lot of the following kind of pictures. So if you don't pay any attention to the pictures later on, pay attention to this very simple cartoon because it sort of sets the stage. Okay, so if I have a general stress tensor sigma ij, I can find eigenvalues. That gives me sigma 1, sigma 2, and sigma 3. It's a second rank 3x3 tensor. So there are 3 eigenvalues and 3 eigenvectors corresponding to orientations. So any stress state that I choose to apply, I can describe as a point in this stress space, okay? So this is sigma 1, sigma 2, sigma 3. The diagonal line here is the pressure axis. So any point along, so as I go along this line, I'm increasing pressure. Any plane that's perpendicular to the line has exactly the same pressure. And so the way I vary the deviatoric stress is I fix a pressure and I just go out some radius and some angle relative to some external coordinate system relative to that. So in the deviatoric plane, I've got 2 degrees of freedom, the radius and the angle. So what I'm going to be doing a lot of today is looking down on the deviatoric plane, looking along the pressure axis, and looking at one plane, the next plane, the next plane. And that's how I'm going to represent stress. Okay, so that's the formulation, how we're going to look at this. And I also want to remind you that the stress tensor has 3 invariants. It's a 3x3. 3 invariants with respect to rotation. The pressure is just the trace. So it's just sigma 1 plus sigma 2 plus sigma 3. And the The second invariant is just the product of the deviatoric stress, with the 3/2 and the square root. And the reason I write this down here is the radius here, from the distance from the pressure axis, is that radius is just the von Mises stress with some constants thrown in just for, just to keep the notation consistent with what most people do in the literature. Okay, so if I look at the radius of where where the transition occurs on the deviatoric plane, that is going to tell me basically the magnitude of the shear stresses. Okay, I'm almost there, and then we can start talking about some results. Okay, so this picture here is one of those deviatoric planes. So these axes, sigma 1, sigma 2, sigma 3, those are the principal axes just looked at in projection. Okay, so we're looking at these 3 axes in projection, and this squiggly circle here is meant to represent the one deviatoric plane at a particular pressure, P is equal to Pi. And this is for the alpha phase. Now, the thing is, I can't actually get any stress I want, any shear stress I want, because the material has a finite yield strength. And so what I'm drawing here are yield surfaces at different values. So these are just yield contours, 1, 2, 3, 4, 5. And if the material has a particular strength, it just chooses one of those yield surfaces. And if the dashed line shown out here is the theoretical strength or the theoretical yield surface of the material. And I'll talk more about that later on. So the yield strengths, or how far we can go out, just go anywhere from 0 if the material has a 0 yield stress, all the way out to whatever the theoretical strength is, which is roughly the shear modulus over 2 pi, which actually turns out to be a pretty good estimate. Okay, so that's one material. So, that's my alpha phase. And so if we're talking about iron, that's the BCC phase. And the daughter phase is a different crystal structure. And it has its own set of yield surfaces, which represent its own symmetry. And so these are the yield stresses for the phase beta, for the daughter phase. Okay, now, if I know those two things, I can say, what is the condition for a transition from an alpha phase, an alpha grain, to a beta grain? Okay, and it's actually quite simple. We need 2 things. We need that both the alpha crystal, at this stress state that we're talking about, sigma, lies within the yield surfaces of both the alpha and the beta curves, of the alpha and beta phases. So what I'm showing on the left is the yield curve for, at a particular level, for phase alpha in blue, and the yield surface for phase beta in red. And so any point that is accessible has to lie within both of those phases, both of those yield surfaces. And the other condition, which is, I guess, is sort of the more obvious one, is we need a free energy, the phase transition, also to be negative, as a delta G to be negative. Okay, so first we need a stress for which the phase transition could happen, that's delta G, and we also have to make sure that that stress is achievable. That is, the stresses lie below whatever the yield strength of the material is. Now, the reason I'm drawing all those different contours here for the stresses is because a given material, the yield strength of a given material depends very much on its microstructure. Okay, and since it depends on its microstructure, by adjusting the microstructure of the material, I can shift how much yield stress, how much shear stress I can apply. It must be less than the yield stress. Okay, so let's talk about some specific cases. I'm going to talk about the iron case, which is the alpha to epsilon phase transition, or BCC to FCC. The classic crystallographic orientation relation you see in these high pressure experiments is the Burgers relation. And so the Burgers orientation relationship is the one shown here. That is the 110 plane of BCC, the high density plane, is parallel to the basal plane of the hexagonal material. And the 111 direction of BCC, the closed pack direction, is parallel to the 2-bar 110 in the HCP. So that's called the Burgers relation. And I would say, if I look at all those possible orientations, there's 12 ways to do it. So if I start with a BCC crystal, it could transform to a hexagonal material with 12 possible different variants, okay? Now, the other case I'm going to look at later on is titanium and nickel. And titanium undergoes an HCP to FCC transition, one application of pressure. And nickel undergoes an FCC to HCP transition as a function of pressure. And here the orientation relationship is the basal orientation relation. And that's shown here. Closed packed here, closed packed there. 111 in FCC, basal in HCP, and again, the same sort of closed pack direction in the FCC and the 112-bar-O in the HCP. Okay, and that's shown here. Now, these transitions, HCP to FCC or FCC to HCP, have 24 possible variants. Now, which variant is the system going to, which of the variants will the system transform to? Well, the answer is a priori, I don't know. It's going to depend on stress. Okay, so we're going to have to consider all possible variants. So this cartoon is actually data. I'll be more specific later on. But so let's look at iron again, the BCC to HCP transition. So we know that iron BCC, alpha phase at low temperature and pressure. And if I look at the transformation surface, which is to say inside this cone, the material is body-centered cubic. That is, if I go all the way down to the origin at 0 stress, it's body-centered cubic. And outside the cone, it's the more dense phase, which happens to be the epsilon or closed packed HCP phase. Okay. The vertex of the cone right here is right on the pressure axis. And that point is along that axis at 9.6 GPa. But experiments show that the value can actually be between 8.5 and 15.6. And we'll come back and talk about that in a little bit. And if I look at this a little bit more carefully, and I look at where this is the minimum, as a function, what the transformation pressure looks like as a function of shear stress. And the shear stress means going out radially. So if I start on this axis, this pressure axis, I go out radially. I go out radially along the deviatoric plane until I hit the yield surface. And I find this relationship here. Now, the interesting thing, and the thing I want to point out to you, is these are all in GPa, but the thing to note here is this value, this coefficient from DFT, is about 1, which is to say that the hydrostatic stress and the shear stress are equally important in the phase transformations, okay, because the coefficient is 1. Okay, so that's an important conclusion. So shear stresses really do matter and they affect the transformation pressures. So if I look over at the experimental data where you go from 8.5 to 15.6, it makes sense that's corresponding to different von Mises or shear stresses here. And so since their coefficient is 1, it should be a similar size. Okay, now, first, if I look at the energy difference, the free energy difference, as a function of pressure of the BCC and HCP phases, delta G, what you can see is that when I make the stress, as I increase the pressure, when it comes to about 9.6, then delta G 0. So that's right there, okay? If I increase the pressure farther, then it wants to be HCP, and if I do it less than that, it's positive, and it doesn't want to go under hydrostatic pressure because delta G is greater than 0. So what we have to do by applying a shear stress is to make up for this energy difference with mechanical work, okay? And so that's basically what the game is. Provide the mechanical work by shear to shift the curve. So if I increase the shear, I'm basically changing the orientation or the slope of that line. And it's going to rotate around this 9.6 number, which is the 0 shear stress case. Now, if you look at a pressure of 5 GPa here, it turns out to, just give you some numbers. So if I go from here to there, that difference in energy requires me to apply a shear stress of order 4 GPa to overcome that enthalpy or free energy difference, okay? So those are pretty large stresses. So we'll see what we can actually achieve. Okay, I've got 2 quick digressions and then I'll get on and start showing you a lot more data. First, all the calculations I show you, all the DFT calculations I show you are going to be done fast. It's all GGA, PBE. The energy cutoff's around 700 volts. The reason I'm telling you a little bit about the details of the DFT calculation is for many of the things I'll show you in a minute, it's very sensitive to how well you converge the calculations. Especially when I start telling you about things like theoretical strengths. Okay, so what is the theoretical strength of the material? So if I take a crystal and I apply a shear stress, and at some stress, I can no longer maintain that stress value. Strain will just go to infinity, which is to say the DFT calculation cannot converge at that stress level. So this is a mechanical instability, okay? So I can do this. A few other people have done this with DFT. There's a group in Czech Republic that's looked at this. A few other groups have looked at it. But the point is, what I'm showing you here, again, this is the deviatoric plane. Again, these are the projections of the eigenstresses, or the principal values of the stress tensor. And these are actually data points, and the curves here shown here. I'm just showing 1/6 of the circle because I know the symmetry. And the point I'd like to make is the theoretical strength here is at least about, what is that, about 13 or so in terms of the GPa, in terms of the von Mises stress. So it's quite substantial. And this theoretical strength curve has threefold symmetry plus a reflection. So that's how we get this curve here. Classically, we always say that the theoretical shear strength is about G over 2 pi, which turns out to be about 13 GPa, which doing the DFT calculation shows that number is like right on. I was actually surprised how well it worked. So it depends on the orientation. So I go here, it's about 13. If I go there, it's about 16 or so. So it depends on what the orientation is. But G over 2 pi is not a bad number. Okay. But the point I want to make is this theoretical strength means that's the maximum shear stress I should be able to apply in principle. It turns out that it's quite large. And I can guarantee that along this line where the system loses stability, no elastic theory could possibly get that right. It doesn't matter how high order the theory is. So, second order, third order, fourth order, fifth order elasticity cannot get it right. So the question is, how well does elasticity work here? And I'm going through this because I'm going to use it later on. So let me show you how well it works. Okay, so this is now the pressure for the transformation, and that's the shear stress for the transformation. So down here, the material iron will be BCC. Up here, it would be hexagonal, HCP. And the green curve here is what I get from third order elasticity. The magenta curve there is what you get from DFT. Now, I just told you elasticity, no matter how high order is not going to work very well. Well, that's true if you know the theoretical strength, but this is at about half the theoretical strength. And actually, third order elasticity does a pretty decent job. So second order elasticity is really not that good. So normal linear elasticity is not that good. So here we applied an arbitrary strain and just increase its magnitude, alpha here, arbitrary strain tensor. And what you see here is the energy is a function of strain. The red points are DFT. The green points are second order elastic from second order elastic constants. The blue curves are third order elastic constants. And so by the time you get to third order, you do pretty good job of reproducing the DFT. So what we're going to do is use the third order elastic constants in order to simplify the calculations we're going to do with DFT. So I'll show you that in a little bit. There is a warning here, is that if you look in the literature for third order elastic constants, I can assure you that more often than not, they're wrong. And I don't care whether you're talking about experiments or DFT calculations. And the reason is, if you look at the experimental data for third order elastic constants, the variation is tremendously large. And if you do DFT calculations, it's very sensitive to what your cutoff energies are. It's very sensitive to exactly how you do the fitting of the curves in order to extract the third order elastic constants. So you can do it. It's not that big of a deal, but we were talking about talking to some of the people who do this for the materials project, and a lot of what they were doing just doesn't work. So you can do better. We know how to do it. And by the way, we have a Python script that does it. It doesn't matter whether you're doing quantum espresso or VASP or whatever. So there's, if anybody wants to do it, just contact us. We're happy to share the scripts. Okay, so that's a digression. Okay, so up to now, we're talking about perfect crystals. But some of the data and most practical materials we use are polycrystalline, except in very special cases. So what we want to do is say, well, what can I say about a polycrystal under stress? Okay. So if I take a polycrystal and I apply a stress and actually look at the stress distribution within it, you see that stresses vary quite substantially from grain to grain, as well as, or strains for that matter, as well as even within the grains. So, how do we deal with that? Well, we're going to cheat a little bit. So if I have a good constitutive law, I can just do finite element calculation and get all this variation. On the other hand, I can get bounds on the problem. There's the Sachs bound and the Taylor bound. One basically assumes that all grains of the crystal are under the same stress. That's Sachs, and Taylor tells it all grains of the polycrystal are under the same strain. Neither one is right, but those are the limits. Those are the bounds. So then the Sachs model provides a lower bound, and the Taylor model provides an upper bound. Okay, and that's a rigorous statement. So what we're most interested in is the onset of the phase transformation. So we're interested more in the lower bound. So we're going to use the Sachs approach. Okay, it's an assumption, by the way. You can do better if you really want to do the finite element calculation, but it's then it makes the DFT calculations too hard. So you can judge for yourself how well this works in a few minutes when I show you the results. Okay, phase transformations in polycrystals. So if I take a polycrystalline material and I look at the free energy of every grain under zero stress, well, the alpha phase and the beta phase have the same energy. So these are just two delta functions, independent of the orientation of the grain, okay, because its stress is zero. Now, if I apply just some arbitrary stress, then the distribution of macroscopic stress, the distribution of energies that you would get for the two phases now starts to spread, because for an arbitrary stress, different crystals are oriented different ways. And so I have to look at the whole rotation of the elastic constant tensor. And so in principle, I could go over all SO3. Okay. Now, if I increase the stress monotonically, I just make whatever the stress tensor I'm applying and just increase its magnitude, what's going to happen is these things are all going to shift to higher energy. So the mean will shift to higher energy and the distributions will broaden. Okay. So that's what we show here is, so at zero stress, all grains have the same energy in the same phase. And as you apply larger and larger stresses, distributions shift to the higher energy density, and also the width of the distributions increase. Now, if I look right here for a minute, it says a grain here in alpha would lower its energy if you allow it to shift to transform to a beta phase, which has an orientation corresponding to this energy. So there's a range of orientations that thermodynamically an alpha grain can transform to in beta. So any of those orientations. But if we say there's only particular orientation relationships, that means for every grain, there's, well, depending on which transformation, we're talking about 12 or 24 different possibilities. And then we look at all possible orientations of grain alpha. So if a grain in alpha has this energy, it can then transform to specific orientations here, as long as they're underneath, they're under here. Okay, so which specific ones just depends on what orientation relations we specify. Okay, so now as I increase the stress, the overall stress level, you get more and more overlap, and therefore more and more alpha grains will transform to beta. So we can look at that. So we can ask the question, what fraction of the grains in the parent phase, I think a polycrystalline alpha material, and I allow it to transform to beta if it wants to, for some arbitrary stress tensor. Okay? So I'll show you how to do that in a moment. I'll show you data in a moment. So how are we going to do this? So what we do is we calculate the third order elastic constants using DFT. So, and then for a particular point in stress space, what we do is we determine the enthalpy of all possible grains in the alpha phase under that specified point in stress space. And at each of those points, we look at all possible transformation variants, all possible daughters, given the orientation relationship. And we say, do any of them have a free energy that's a change in free energy, which is negative? Okay, and if it does, that says it can transform. And so at a particular point in space, I'll have say 35 different orientations of the alpha phase that can transform, and it'll transform to any of those daughter grains. Okay, and I can repeat this for all points in stress space. And if I want to find what is the minimum stress I can apply in order to get the phase transformation, all I do is find the parent grain orientation that has the highest energy. I keep increasing the stress along that radius vector in the deviatorial plane, and we look over all possible grain orientations, SO3, and find the lowest energy daughter variant. And from that, we can find which, in that particular stress path, I can find out what the minimum stress is for the transformation to begin. Once I have that from this DFT-informed nonlinear elasticity, I can go back and verify this with density functional theory along that whole transformation surface. Okay, so data. So what I'm looking now is in iron. I'm looking at percent transformed versus stress state. So each of these plots you see here is 1/6 of the whole stress space at a particular pressure. And then these 6 different plots are at 6 different pressures. And let's just pick one here at 8 GPa of pressure. At 8 GPa of pressure, as I go out, increase the shear stress, it's the von Mises stress, eventually I cross the line where the transformation can start. The white solid line is the prediction from the third order elasticity, and with the DFT data for the energies of the phases and the elastic constants, and the dashed line is the direct DFT calculation. And what you see here is the percent of grains transformed as a function of shear stress in different orientations. Okay, and so that's shown here. And as you go to higher and higher pressures, you can see that this envelope gets pushed down to almost 0 shear stress. And in the limit, you go to 9.56 GPa. This goes to 0, which is to say it'll transform and I don't need any shear stress. On the other hand, if I lower the pressure to about 5 GPa, you can see that the transformation takes place. The percent of grains that transform is very small at low stresses, and only a very small fraction, 2, 3, 4% will transform for shear stresses as large as 5 GPa over here. And as you go to higher pressure, what you find is the fraction that gets transformed at a given stress level increases. So that's what's shown here. So as P goes up, larger compression, the fraction transformed at a given shear stress increases. And that's the curve here. So one of the things you see right away is the transformation pressure is very shear dependent, or the shear that you need to apply to get the transformation is very pressure dependent. Either way. And the reason is quite clear, because iron, if I look at BCC to HCP transition, the volume difference is substantial, and that volume difference is what gives you the pressure effect. The other conclusion is if I compare the elasticity result with DFT-informed elasticity with a full DFT calculation along the entire surface, what you see is that it's not too bad. So third order elasticity seems to work okay. Now, let's shift to nickel. And nickel is an interesting case because first, these are stresses that go from +5 GPa compression to -5 GPA, which is hydrostatic tension. I'm not sure if one could do that in an experiment, but probably not. But the point is, one of the things you see here is that in nickel, because I'm going from a closed packed structure to a closed packed structure, FCC to HCP, there's very little shear stress dependence to it. So it's almost pressure independent. It's almost, the shear stress needed to transform is almost pressure independent. And again, DFT seems to work well. I'm going to go back and compare this with the experiment in just a minute. Okay, here's titanium. Titanium is HCP to FCC as you increase the pressure. And again, you see very little pressure dependence. This is P equals 0. And if I look at the transformation shear stress as a function of pressure, it's almost pressure independent. Okay. And again, DFT seems to work pretty well. Okay, let's go back and see how this does compared to the experiment where I have data. Okay, so let's focus first on iron. The transformation pressure in iron is very sensitive to shear stress, as I talked about before. The difference in volume per atom in the two phases is about 1 cubic angstrom per atom between the BCC and the HCP phase at 0 pressure, quite large. And so that gives you this curve. So very strong pressure dependence. Now, if I go back and look at the data I showed you earlier on, as you go to higher and higher strength pressure media, that means I can have higher and higher shear stresses. And so as you go up in yield strength, you're going to go to a much larger range of shear stress you can get, and therefore a much larger range of transformation pressures, which is sort of consistent with this. The larger the shear stress you can put on, the more you can shift the pressure. Okay, so that's that. So the theoretical shear strength of this material is about 8 GPa. Sorry, that number looks wrong to me. And so in principle, one should be able to achieve the transformation at pressures as low as 1 GPa. But it never happens. It never goes down to 1 GPa, and that's because we never see yield strengths up as high as the theoretical shear strength. Okay, this is my favorite experiment. This is the one that I mentioned. This is from the group in Shenyang. So this is the paper I showed you in the beginning, where you saw that some grains of this polycrystal under this severe plastic deformation that you get, some of the grains transform to HCP rather than stay FCC. And we can do a little bit of analysis on the data they provided in this paper. So they found that some HCP grains are only observed when you've got grain sizes smaller than about 17 nanometers. And so if I look at where the grain size is of order 17 nanometers, it's about 12 microns below the surface. If I read up to 12 microns below the surface, I get a hardness which is about 6 GPa. If the maximum yield stress, if the yield stress is about the hardness over 3, sort of typical values you use, that suggests that the stress is about 2 GPa where the transformation occurs. It doesn't mean that the stress is actually 2 GPa, but it can be as large as 2 GPa up to the yield strength. Okay, so it would seem to suggest that the FCC can transform to HCP for shear stresses above about 2 GPa. And if you go back to the curves here, this transformation actually starts at 1.6 GPa according to the DFT calculations. So that I'd say is remarkably consistent. You know, within a factor of 2, I would say it's probably good enough, but that's you know, that's like 20% kind of value. So pretty good agreement. The other thing that they found in this paper is that as you go closer and closer to the surface, the grain size gets even smaller and the hardness goes up even farther from about 6 to about 7, 8, 9. So that means that you can have shear stresses, which are about a third that. So at shear stress about three, it would say that right at the surface, it should be possible to get something of order, 70 or so, 70% transformed. Okay, and they also found they get more HCP grains to get closer and closer to the surface. Okay, so the one value we can actually make a direct comparison that's pretty reasonable, and the trend is also pretty reasonable. Titanium, well, it turns out I don't really have much good data on titanium that I can find in the literature. But if you look at these channel die compression experiments, where you deform material and the shear, the grain size gets remarkably small, and the stresses that you can see suggest to be at least around 0.7 GPa there, and that's where they start seeing the HCP to FCC transition. If you look at a compressed nanopillar, in some regions of the compressed nanopillar, you can see HCP to FCC transition. And if you do ball milling, which is high energy mechanical attrition, you get grain sizes of order 5 nanometers. And when it gets that small, then you start seeing some of those grains transform to HCP. Okay, unfortunately, our value is about 2 GPa, and it's to be pressure insensitive, but there's no data here to really make a quantitative comparison with. But the trends are the same. As you go to higher and higher shear stresses in titanium, you get more of this HCP to FCC transition. Okay, this is my last slide before I put out the conclusions. So I think I've been talking a little bit too long already, but only one slide beyond this one. Okay, so if I look at the iron, nickel, and titanium data together, what do I see? So first, iron is the only one of these 3 systems for which the phase transition is pressure sensitive. Nickel and titanium are very pressure insensitive. And again, that's because the phase transition between BCC and HCP iron has a big volume change, therefore a large pressure difference. That's the P delta V term. If I look at nickel and titanium and compare them with each other, you see that titanium has a much higher shear stress required to get the transformation than nickel. And that's a little bit surprising because nickel has higher shear moduli than titanium does. But we can understand that because if you look at the difference in enthalpy between the FCC and HCP phases of the 2 materials, you see that for nickel, the enthalpy difference is about 0.025 EV per atom, and for titanium, it's more than twice that, which means the applied shear has to do much more mechanical work in order to get the transformation from FCC nickel to HCP nickel. HCP titanium to FCC titanium. Then I need to go from FCC nickel to HCP nickel. So again, that ordering is consistent with the experiments. I mean, with the DFT calculation. Then it makes sense. Okay, so let me conclude. So as we all know, and we sort of saw, at least I saw it first time in my solid state physics class, that many materials undergo very high pressure induced phase transitions. And usually we neglect shear stresses. And the reason we neglected it traditionally is just that you can't apply large shear stresses because the yield strength of the material is usually limited. The material either flows or in some cases the material will fracture. But these days people are making all sorts of interesting microstructures with ultra high strength microstructures. nanotwin structures and these gradient structures. And if you look in the literature, there's lots of hints of things that suggest that shear stresses that start to play a role if you can get the shear stresses large enough. In polycrystals, one of the interesting things is that some grains will transform under a given stress and some will not. Well, that's just because, unlike pressure, shear stress depends on the orientation of the grain relative to the shear axis, relative to the shear, the shear stress, the particular orientation. And so some grains will be more favorable than other grains. And that can only happen if it's a shear-driven effect, not a hydrostatic stress-driven effect. Now, you may ask, why didn't I just do molecular dynamics for this instead of DFT and all that elasticity? And the bottom line is most interatomic potentials are not fit to very high strains and very high stresses and multiple high stress phases, like the epsilon phase in iron, for example. So our approach was to use DFT and nonlinear elasticity to identify transformation surfaces and the fractional grains transform for all possible stress states, and then to go back and verify those transformation conditions directly with DFT. So the nonlinear elasticity provides a guidance that makes this calculation much smaller. So we looked at 3 metals, iron, nickel, and titanium. And one thing you found is the transformation pressure for iron is strongly shear dependent. So we found it's consistent with the experiment. For nickel, titanium, transformation volume effect is negligible. And titanium versus nickel, the fact that you need much larger shear stresses for titanium than nickel is just due to the energy difference between those two phases in those two different materials. So we can understand piece by piece. Okay, and then the thing that I'd say, the part that really originally motivated me to do this work was this very nice set of experiments in nickel done by the Shenyang group. And in that case, I'd say our agreement with the experiments is quantitative. I would say we could probably be quantitative for many more materials. There's just not a lot of good data at very high shear stresses. Okay, so I've told my whole story. I welcome questions and any comments from anybody. If you don't have time to do it now, you can contact me later and critique this for me. It's the first time I've had the opportunity to talk about this topic, so please feel free. I'm done.
All right, thank you so much, David. That was really a very nice talk, and even I, as a total outsider to your field, could sort of kind of follow along. So
I guess that's kind of good.
Yeah. There were a couple of questions in the chat, and I'll just read them out for you. So first question from Lindsay Greer, who writes, David, great talk. From thermodynamics to kinetics. We are familiar with effects of hydrostatic stress on kinetics, activation volume, etc. How much should we be interested in effects of a deviatoric stress on kinetics?
I should say, David, sorry, of course, you were talking about a situation where kinetics were not of particular interest, diffusionist transformation, 0 Kelvin. But is there a whole other room out there where we should be interested in deviatoric stress having other effects?
Yeah, right. Interesting question. So first, actually, even in the diffusionless transformations, these Martin-Siddick type transformations, there's still a question of what is the barrier. And I really didn't address that in when I originally wrote the proposal for this. That's what I told them I was going to spend most of my time on, is the kinetics. but I haven't gotten to it yet. And now I've spent half the money already. Now, but then that requires understanding the effect of stress on the barriers and on the transition paths. And I think, we should be able to do it just like we know that there's an activation volume for things. There isn't, depending on how you want to say this, there's a lot of languages for this. There's an activation strain tensor, right? And that activation strain tensor certainly does have shear components, because the transition paths tend to be shear paths. Now, if you now go to cases where the transformation has a diffusional component, then I sort of have to ask about what is the effect of shear on all of the diffusion constant tensor. It's an interesting question. I would imagine somebody's looked at it. I haven't, but maybe Lindsay.
I think there's been a little bit of work on diffusion in silicon that shows it's accelerated under shear stress.
Yeah, that was the Harvard group?
Yes, correct. Yeah.
Yes, right.
There is something there already.
Yeah, I vaguely remember that work. I forgot about it now. But yeah, thanks for reminding. I should go back and look at that. Yeah, diffusion, non-Martin-Citic or or diffusional transformations, I think are a whole other game here. Yeah. The other thing I would say I would suffer from if I did that is the issue associated with, if it's diffusional, I don't necessarily have these as strong of an orientation relationship. So if I have one grade here, it's going to transform to another one. That means I have to look at all possible orientation. It means I have to do a search over all of SO3 in the alpha phase, and then for each one of those do a search over SO3 in the other one. And that's a 6-dimensional calculation at each point in stress space. So the bottom line is, it's ugly. It's a good question, but I'm afraid of it.
Okay, thank you.
Okay.
Okay. Another question from Leo Ma, who writes, how should temperature be considered? Inside the diamond anvil, the high pressure should do work on the sample and heat it up. Your current model seems not to be considering the free energy, but only the energy.
Yeah, absolutely. I mean, it's 100% correct. Yeah, we've done it in a few cases where we've thought about putting in all the vibrational components to it. We know how to do it. It's just expensive to calculate the vibrational contribution to all of this. In any particular case, you can do it. It's fairly straightforward. Most of the, in all the major DFT codes, it provides you ways of calculating the dynamical matrix, and from that getting at least the quasi-harmonic version. So I think we can do it. And I don't mean to say that it has no effect, but I think it's worth studying. It's the whole extra dimension in the phase diagram, the temperature dimension, which we haven't explored here. It's an opportunity. This is the only thing we've done so far. So if you're interested, I'd be really interested in working with anybody who wants to actually bite the bullet and actually do the problem. I think it'd be very hard to do as a function of all of the stress components, simply because the real problem, because that each problem is kind of computationally intensive. I can't even begin to tell you how many hundreds of thousands of DFT calculations went into that little bit of data I showed you. Mostly very small, but still a lot. Real exercise in Python scripting.
Very Very good. There's another question asking about what kind of behavior would we expect from austenitic stainless steel alloys?
Yeah, well, okay, so steels are going to be more complicated, obviously, partly because of it's two component. That's at least two components, and the micros. You know, we have to worry about all the different forms of the microstructure. Normally, I don't know. I could sort of sit here and try to figure this out, but I don't really know. I haven't really looked at it seriously yet.
All right.
It's a good question, and it's obviously very relevant to all the martensite issues. The FCC to BCT. Yeah, I don't know. I have to. Yeah.
Okay.
Duly, I note the question. No,
we'll invite you back once you know the answer.
Yeah. Right.
Last question. How is the stability of the transformed phase against temperature or stress during service?
Okay, so I'm not sure. So obviously it's going to depend on the situation, but let me say a few things. So in some of these materials, in the case I looked at here, a low temperature, the high pressure phase is at least metastable. Okay, so which means when you release, if the stress gets released, the structure could stay. Okay, so at least it's metastable. That's the first point. By the way, if you look at titanium, and if you look at the HCP to BCC transitions when you raise the temperature, that's a bit of a dog, because BCC is not even metastable at low temperature. It's just unstable. So generically, I don't know the answer to that, and I'm not sure there is a generic answer to that question. And also changing temperature. Yeah, we haven't looked at temperature yet. Like I said, this is the first time, this is our first exploration of this. So I'm usually more comfortable giving talks after I've worked on something for 5 or 8 years. But this is a year's worth of data, and so there's a lot to be done. So I don't want to oversell it. So
Fair enough.
It's a good question. So I don't know, and in fact, a lot of this question is, for example, is the way Lindsay asked the question. There's kinetics to this as well, and the kinetics, the effect of shear on the kinetics, not very completely studied, except for the one case I know of in silicon, the Harvard work I mentioned from 25 years ago, maybe even longer, I don't even remember. Michael Aziz's work. So. Okay,
well, I think we have no more questions. Thanks for a wonderful talk. And unfortunately, no beers or anything afterwards. So that's
I'm gonna come back and get my beer later.
Yeah, that's where it has to end. Thanks everyone for joining, and have a good rest of your days. Bye-bye.
Okay, thank you.
Bye.
Thanks all for coming.
Bye.
Thank you.